Welcome back. This is kind of a review lecture, but more so we'll see a bunch of examples, right? So we started the course by looking at various models and things like that, and then we eventually understood how to um, basically look at some kind of existence, guaranteed of existence of solutions for this particular differential equation, where I'm sure you by now you know that x of t is a function in mapping our Rn to R to Rn, where the input is time, t is time, and then this x dot is the time derivative, and we understand that this particular ODE has a solution if f is continuous, right? However, we cannot have any guarantee of uniqueness or anything like that. So we needed additional condition. Continuity simply guarantees existence. Lipschitz continuity gives existence and uniqueness, right? And in nature, in physical applications and things like that, we typically expect our models to have unique solutions. Rarely we have some examples where we have multiple solutions. Then of course either of them are kind of local results. Existence of solution could mean multiple solutions in a small range of time. Lipschitz continuity gives you existence and uniqueness in again possibly a small space region around the point that we're starting, as well as time, right? But if we want some kind of global guarantees, then we typically assume f is continuously differentiable with bounded derivative, for example, right? Then we have global existence and uniqueness, right? So when we present all the theory, we kind of assume that we do have this global existence and uniqueness. Sometimes the global nature in space it works, but in time we may have finite escape time and things like that. So then we went on to look at the dynamic behavior of these solutions, and then eventually we said we'll make a standard assumption that there is an equilibrium at the origin, right? In case in our physical problem, if the equilibrium point is not at 0, we can shift the coordinates or modify the theory. I mean, it's relatively straightforward to do that. So once we do that, then we defined Lyapunov stability, asymptotic stability, and then of course exponential stability. And if these none of these are true, then basically we'll have instability, right, or unstable equilibrium point. So, but then these definitions of stability involved epsilon delta type definitions, and therefore they're quite difficult to test. So then we brought in our main hero of this particular course, Lyapunov. And Lyapunov, more than 100 years ago, he presented these beautiful theorems that go something like this. If you have a function that is positive definite, that means v of 0 is 0, and then v of x is positive for all non-zero x, and we call these two conditions put together as Lyapunov function candidate. And the next one is basically if we have this v of x defined as v gradient, inner product of gradient in this F matrix. If it is less than or equal to 0, then we have Lyapunov stability. And if we have strictly less than 0, then we have asymptotic stability. And if we have v of x upper bounded and lower bounded by some kind of I don't know, norm, okay, and also we have this v dot less than or equal to minus epsilon v, where epsilon is positive here, then we have exponential stability, right? So all these are good, but then one of the more difficult aspects is to finding this Lyapunov function. So therefore, if we do finding Lyapunov function, many cases what may happen is we may get this condition, right? And then can we conclude asymptotic, or can we gather rather, asymptotic behavior of this system? And the answer lies in this beautiful theorem and beautiful theory provided by LaSalle, Barbachan, and Krasowski, and we loosely call it as LaSalle's invariant set theorem, right? I mean, prior to that, basically without even thinking about any Lyapunov functions kind of a thing, there is a beautiful theorem that says the limit set, positive limit set, omega f x is non-empty, compact, connected, and invariant, right? So knowing this, along with the fact that there is some function which is decreasing always, which is lower and upper bounded, we can conclude many things in terms of global behavior, right? So of course, knowing existence of some function and having some stability or boundedness is nice, but what about how do we prove instability, or can we guarantee existence of some functions and things like that? And we saw converse theorems, and then of course we saw instability theorems, right? And these are not easy to remember, any of them, but they're quite complex. But if you have a book in front of you, one can go through those things, right? So anyway, this is the summary of basically last several lectures. So let me actually solve a bunch of problems, and one may pause every now and then to see how to think about these problems, right? So the first problem is nothing to do with stability or anything. It's important that students going through nonlinear systems course understands how do we show continuity and things like that. Um, more importantly, Lipschitz continuity, continuous differentiability, and things like that. But here I'm going to show primarily how to show continuity, right? Here is a very simple example where we have f of x is given by these functions. When it is 0, it is 0, and then when it is not 0, then x square sine 1 over x, okay? And the continuity example is also, continuity definition is also in terms of epsilon delta, the nature of it. If you want to quantify it, you cannot say, lose language to make it very precise. The best thing to do is using this epsilon delta definition. Now there is an alternative. One can define continuity to be, so for example, one of the definitions is you can interchange limit like this. So f of limit of going x of x going to x0 or something like that. And if this is satisfied, then we can conclude that x is f is continuous at x0. But this too, the limit definition itself is dependent on epsilon and delta type of definitions, right? So it's quite painful at times to show continuity from basics, but there are many techniques that we use, and especially knowing certain things, like for example, all polynomials are continuous. I mean, somebody took the pain of showing all polynomials are continuous, and we will take that as a fact. So once we know something is continuous like that, then we can actually do tricks like this. So for example, x square sine of 1 over x, okay, is less than equal to x square. Why is that? Because sine of 1 over x is between -1 and +1, so this is always guaranteed for whatever value of x. And then similarly, this is true also, right? So as x tends to 0, you can clearly see this both sides, minus x square and plus x square are going to get closer and closer together, and therefore x square sine of 1 over x is in between these two. We can conclude that this is true. X squared times sine 1 over x is going to go to 0, right? I mean, more generally, if x square is multiplied by any uniformly bounded function, meaning this is between -1 and 1, no matter what the value of x is, and those bounds -1 and 1 are independent of where my x is, you can easily conclude that x squared times some uniformly bounded function is always going to go to 0 as x goes to 0. So this essentially shows that limit x goes to 0, f of x is going to be 0, which of course is f of 0, right? F of 0 is 0, so therefore f is continuous at 0, right? Yeah. So that's the first example. Let's move on to, I have this additional empty pages, but doesn't seem to require some of these things, right? So the second example is showing exactly the opposite, discontinuity, right? So how do we show discontinuity? We show that these limits, as x go to x1, x2 goes to 0, they're not necessarily going to be equal to f of 0, right? So even in this particular case, we have f of 0 is 0. In this case, it's two-dimensional. F of 0, the 0 means 0, 0 in the two-dimensional version of the origin, right? So we need to show that as a limit f of x, as x goes to 0 is not going to be 0. But the thing is basically, when you have a two-dimensional system, let's say, you can have limit going this direction, this direction, this direction, perhaps going some other way. All these possibilities are there, and many of them still going to go to 0. Possible, right? Very much possible. But even if one of those limits is going to go to non-zero, then we will end up with discontinuity, right? So let's therefore observe in one particular direction, right? So I'm going to do this trick. I'm going to divide numerator and denominator by x to power 4, and I'm going to end up with this, right? Yeah, so we have this function x1 square x2 square divided by this fourth order summation. We rewrite this as a ratio of these things, and then I'm going to show on the line x1 is equal to x2, right? So that's specifically, let me do it in a different color. So that's just, that's supposed to be going through origin. So that's the line x1, x2, x1 is equal to x2. So we have points very close to 0. But on that line, right, this f of x is going to be equal to 1 divided by 1 plus 1, which is half, right, for all x1, x2 on the line x1, comma, x1 is equal to x2. So that means, very close to the origin on this line, okay, x goes to 0, f of x is going to be equal to half, which is not equal to f of 0, right, on the line. So this function, this function is therefore discontinuous, right? Are there other directions and other lines, so to speak, are going to have this property? Yes. Are there some other lines where this is possibly going to be 0? Absolutely, right? It's not necessary that one direction will give you discontinuity and all the others will give continuity. Discontinuity. So it's possible that you can find a direction in which this particular function is continuous, but that's not the purpose of this particular example. So hopefully you get to see two or three different two problems of continuity, and then understanding how to prove continuity, Lipschitz continuity and things like that is good enough. So take up a few problems from the textbooks that we mentioned and then basically practice them, right? So next problems are more to do with the stability behavior, and so we have this system x1 dot, two-dimensional system. X1 dot is equal to minus 2x1 minus x2 square, and x2 dot is minus x1 square minus x2, right? Clearly it's a nonlinear system. If we take the attitude that let's say we ignore the higher order terms, we can clearly see that x1 dot is minus 2x1, x2 dot is minus x2, and if you can solve that, you can clearly show convergence and things like that. This system seems to be locally asymptotically stable, right? But that's a theorem we will actually prove at a later time, that if you have the linearization of the system, then we can conclude many things from the linearization. But for the time being, we will actually go with the Lyapunov function method, right? So this Lyapunov function, clearly v of 0 is 0, v of x is positive for all non-zero, and then of course more importantly we do have this v of x is indeed equal to norm of x square, right? So that means it also satisfies the basic conditions of exponential stability. Whether this is exponentially stable or not is a different issue. Okay, so now the question is basically what can we say about this Lyapunov stability or asymptotic stability, right? So for that we need to compute this v dot of x, which is nothing but, I'm going to go slow in the first example, it's essentially 2 times x1 times x1 dot plus 2 times x2 times x2 dot, right? And x1 dot and x2 dot are given and you substitute. So 2x1 times minus 2x1 minus x2 square plus 2x2 times minus x1 square minus x2. Okay. So I'm going to get minus 4x1 square minus 2x1 x2 square plus minus 2x2 x1 square minus 2x2 square. Okay. So this is, I'm going to collect a few terms here and there, minus 4x1 square minus 2x2 square, and then we have this cross term. I'm going to just write this as minus 2x1 2 x1 plus x2. Okay, So the question is basically, is this strictly negative or not? For that matter, it is not, it doesn't even seem it is actually less than or equal to 0 because of the cross term here, right? But let's do the following, right? So, you know, let's say x1 plus x2, the norm is less than or equal to x1 plus x2, right? And on a let's say ball small enough, we can ensure that x1 plus x2 is less than some, let's say 1. Okay, so you know, I'm sure you can. So you know, on this region, right, we have that x1 plus x2 absolute values less than or equal to x1 plus x2 absolute values, and if you put a circle inside that, so in any of the circles within this square, we will have x1 plus x2 less than 1, right? So v dot therefore is going to be equal to minus 4x1 square minus 2x2 square minus 2x1 x2. Let's yeah, okay, for all x1 x2 in the ball, right, some ball of radius whatever, right? So but this, it can be viewed as minus 2x1 square minus x2 square minus x1 plus x2 whole square. Okay, so so what can we say? Basically, this is clearly strictly less than 0 for all x non-zero, and this x belongs to this ball, right? Not only that, we can actually you know, take a little bit of more pain and basically conclude that it's also is less than or equal to some gamma times v, right? So this shows Lyapunov stable because it's less than or equal to 0, asymptotical stability, and then the last thing is exponential stability, right? But only locally, right? This is not going to be true globally. Okay, so we have these nonlinear terms, you know, non-quadratic terms that could initially be confusing, but then we took some kind of factorization and showed that that can be bounded by some number, and therefore we can conclude all the nice things about stability of this particular zero sum, right? So we'll continue to the next example. So the next example is, you know, again a second order example, and this time I'm not going to really write the state space version and then show. Sometimes you can be lazy and not going through the state space. By the way, one has to be careful. So we have to go back and look at the examples that we have seen. Are the equilibrium points given by whatever, you know, sorry, you know, set the right hand side to 0 and then get all the equilibrium points to start with, right? So so in this particular example, x double dot is equal to g of x, and one can clearly see that 0 0 is going to be the only equilibrium point, right? The next question is whether this particular system is Lyapunov stable or globally asymptotically stable, sorry, asymptotically stable or globally asymptotically stable, or anything about exponential stability, right? So you know, there's a suggestion for Lyapunov function candidate, which is given by half x dot square plus this integral, right? So it's not necessary that all the Lyapunov functions are of the form quadratic and things like that. So this is one of those exceptions. So you can easily conclude that v of 0 is 0. V of x is positive definite, how do we conclude for x dot part is fine. The fact that g of x satisfies this condition, x times g of x is positive, right? Let's say instead of integrating from 0 to x, imagine let's integrate from point 1 to x or some other x by 2, let's say, right? Since x is positive, x by 2 is going to be positive in that particular case. Okay, and you can clearly see that you are integrating over the positive numbers, and then therefore you'll have at least some positive integral there. So this integral can be shown to be positive when x is non-zero. So now all the nice things about a Lyapunov function candidate, we confirm that it is a Lyapunov function candidate. So the next thing, of course, is basically looking at v dot, right? So v dot is going to be x dot, x double dot, and plus, if you recall basic calculus, then this is simply going to be g of x, right? I believe it was called Leibniz rule, times x dot. So that's nothing but x dot times x double dot plus g of x, which of course is equal to 0, right? So we have v dot is equal to 0, and that implies 0 is Lyapunov stable. So certainly we cannot conclude that this zero solution, the equilibrium point, is asymptotically stable, at least using this particular function. But what can we say anything about, can we use the LaSalle theorem? Well, we don't have any information beyond that. Basically, this is v dot is 0, right? So the only conclusion we can basically say at that particular point is, if it starts at some v of x 0 comma x dot 0, right, the solution is going to remain on that surface, okay, because v dot is identically 0, but nothing beyond that. Unless we know more about this function g, we cannot really say like that. So in that sense, asymptotic stability is ruled out, right? How do I know it's ruled out? Because v of x, if this is not the origin, then v is positive, that we concluded earlier. If v is positive and then we know v dot is 0, the x of t, the solution, is going to remain in level set, and we can therefore rule out asymptotic stability. It's never going to reach the equilibrium point.